Hi, the next series of videos will be on reactions of carboxylic acids and then the derivatives of carboxylic acids. So the first video I wanted to do is simply going through the common carboxylic acid derivatives that you'll encounter in your organic chem class. Number one is going to be an acid halide. Almost always, these acid halides are really an acid chloride. Chloride is by far the most common of the halides used. So what the acid halide looks like is we have our R group, the carbonyl, and then chloride. With all of these derivatives, that is constant. The R group and the carbonyl, it's what's binded to that spot that makes it a derivative, because usually for carboxylic acid that would be an OH group. But for each of the derivatives, it's going to be a different group. And each of these different groups is going to impart a different reactivity. Number two is going to be an acid anhydride. So again, R group, carbonyl. This time, that is our anhydride group. Number three, ester. This is probably the one of the derivatives that you're most familiar with. Rather than an OH, it's OR. And the difference between an OH and an OR is you're not going to be deprotonating an OR like you would with an OH. That automatically imparts a different reactivity, but then also whatever the R group is different in structure and electronics, etc. from a hydrogen. Then lastly, number four is an amide. Again, a functional group you may have learned about already. That would be the amide. Now, each of these four groups differs in its reactivity. If I were to put them in order of reactivity, so the top is going to be most reactive, down to least reactive. My most reactive will be the acid halide. It's greater in reactivity than the acid anhydride. And that's greater in reactivity than the ester, which is greater than the amide. But what makes their reactivities different? Okay. So for the acid halide, there's really two things. One, chloride is an exceptional leaving group. You learned that back with SN2 and SN1 reactions. Chloride's a great leaving group. And secondly, the more electrophilic that carbon is, the more prone to nucleophilic attack it'll be. So if I have an oxygen that's pulling electron density away this way, and I have a chloride that's pulling it away in this direction, on top of the chloride already being a fantastic leaving group, that gives you your excellent reactivity. Now, the acid anhydride, the main thing that's going to give you the reactivity, you'll have some inductive effects from the oxygen right here. Right? There's some inductive effects from that. But mainly, when you attack with your nucleophile to form your oxanion, or oxanion, and then that reforms the pi bond and it kicks off this leaving group, you're kicking off this group, which is resonance stabilized. and it has a negative charge on an oxygen. So that's a very stable leaving group, a good leaving group, and that is why you'll have your acid anhydrides react pretty well. The ester, it's a little less reactive because an OR group isn't as good of a leaving group. You'll likely need to protonate it before it can leave as an alcohol. So that takes a little bit of an extra step. But then you do have, again, some of that inductive effects with the oxygen on the OR group to help make that carbon a little more electrophilic. Then the NH2 group, again, you have to protonate it for it to be a good leaving group, and nitrogen isn't as electronegative as oxygen is. So that's why it's not as reactive as the ester is. So these are the 4 carboxylic acid derivatives that you'll encounter the most as we move through with these videos on the reactions of carboxylic acids and their derivatives.